Welcome to science class. Today we are going to explore the geology of the ocean floor. Some of these features you are familiar with, such as the mid-ocean ridge, which we covered in the plate tectonics videos, and the continental shelf, which we briefly touched on in the last video. But the ocean floor and its geology are much more diverse than that. We don't actually have a good sense of just how diverse it is, since it is so hard to study. You've probably heard that we know more about the surface of the moon than we do about the bottom of the ocean. And that's true, but we haven't directly explored more of the moon than the ocean. The moon's surface is always visible to us, at least half of it is from our perspective. What we do know about the ocean floor is it is entirely igneous, being made of basalt and almost nothing else. We also know that massive piles of sediment from hundreds of millions of years of erosion of land has accumulated on the ocean floor. The closest we can get to seeing the ocean floor, apart from going there ourselves with submersibles, comes from looking at it from outer space. Satellites send radar, which stands for radio detection and ranging, pulses to the ocean surface, which then bounce back. Tiny fluctuations in the ocean surface reveal the shape of the ocean floor. And no, I'm not talking about waves on the surface. I'm talking about gravitational anomalies. In fact, these maps are called gravity maps. An underwater volcano, or mountain, or ridge has more mass and attracts water to it. The surface of the ocean is slightly higher above massive underwater features. Oppositely, the water surface is depressed near deep trenches and other low-lying areas of the ocean floor. If the height of the surface of the oceans was determined entirely by gravity and Earth's rotation, then these differences between what we call sea level around the world would vary by nearly 200 meters. But instead, because of wind and tides and other factors, the variation in sea level only varies by around 2 meters. These tiny surface anomalies in the ocean are detected by the satellite, and then a map of what lies below can be made. This is the most detailed map we have of the ocean floor. Pretty cool, right? Let's get started. We are going to start at the shore and make our way to the deepest part of the ocean. As we leave the shore, the first region we encounter is the continental shelf. Again, this is a gently sloping subsurface feature that extends for hundreds of kilometers in some places, and as much as 1,500 kilometers in other regions. On average, the continental shelf is only around 130 meters deep and extends 80 kilometers out to sea. And here's just how flat it is. If sea levels dropped by only 30 meters, then off the coast of Florida, the new coastline would extend some 60 additional kilometers. That's a massive amount of additional land. And this has happened before. During the last ice age, sea levels were 120 meters lower than what they are today. This made the majority of all continental shelves on our planet dry land. Take a look at this map of what the world looked like from that time. Britain and Ireland were not islands. Scandinavia was not a peninsula. Alaska and Russia were connected. The majority of islands of the Indian Ocean were not islands. This exposed a land area equivalent to all of North America, an entire extra continent's worth of land, and it was only around 15,000 years ago. In many places, the continental shelf abruptly ends and a much steeper continental slope emerges. This is just like the walls of a canyon, just nowhere near as steep as they are on land. Many sections of the continental slope are cut by submarine canyons. These are almost indistinguishable from canyons on land, but they form in entirely different ways. Currents of slightly more dense water, which gets its additional density from sediments, slowly flows down the edge of the continental slope. This gradually carves away portions of the continental slope. Finally, the ocean floor again begins to level out, and we hit the continental rise, which is the region between the continental slope and the almost completely flat ocean basin floor. Together, these three regions, the shelf, the slope, and the rise, are known as the continental margin. The ocean basin floor makes up almost 30% of Earth's entire surface, which amounts to about 43% of the ocean floor. Among the ocean basin floor is the abyssal plain. These are extremely flat portions of the ocean floor. and their flatness comes from a blanket of sediment that lies on the ocean crust. This sediment is thought to be, on average, 1,000 meters thick. Where oceanic plates converge, there are trenches. Most ocean trenches are found in the Pacific Ocean. The deepest trench, the Mariana Trench, reaches a depth of over 11 kilometers, far deeper than Mount Everest is tall. Also found along the ocean basin floor are seamounts and guyots. Seamounts are underwater volcanoes, both active and extinct. Guyots are underwater volcanoes that used to be exposed to land. We can tell they used to be above water because they are clearly eroded on top. This is what distinguishes them from seamounts, which are cone-shaped. There's no difference between a seamount and a volcanic island, apart from the fact that the volcanic island breaks the ocean's surface. When volcanic islands do break the surface, coral reefs may form around them, creating what's called a fringing reef. Volcanic islands do not last forever. As the plate moves the island away from the source of magma, they sink into the sea, but the reef can grow vertically and stay near the surface of the water. This forms what are known as atolls, ring-shaped reefs that contain a lagoon, a body of water cut off from a larger body of water. And finally, we reach the mid-ocean ridge. Virtually all mid-ocean ridges are continuous with one another. Once again, the mid-ocean ridges are produced from oceanic plates that are diverging, splitting apart from each other. The mid-ocean ridge is vast, stretching for 70,000 kilometers, and ranging from 1,000 to 4,000 kilometers wide. Among the mid-ocean ridge are many hydrothermal vents. These are areas close to Earth's mantle where water is drawn in, then shot out at very high temperatures, and heavily laced with minerals. Chimney-like structures around hydrothermal vents form as the many dissolved minerals precipitate once they reach the nearly freezing waters of the deep ocean. There is likely much more to learn about the bottom of the ocean. Expeditions to the bottom are rare, but they always produce brand new scientific insights, especially when it comes to discovering new species. There are also resources at the bottom of the sea that could theoretically be used, but it's not practical or cost-effective to gather them. I happen to think the fact that it is such a mystery about what's down there makes it so intriguing. Who knows what we will discover next? Next time, we are going to study the different types of ocean currents. Thanks for watching.